Okay, so I want to do something different. So I'm going to follow Griffiths, but we've decided we're not going to go into as much math as Griffith gets into in chapter 1, but we will talk about the math as needed. So my thinking for today is I'm going to show you what we were doing yesterday and try to apply it to a few things. Okay, so if we go back to what we were doing yesterday, we did ordinary derivatives. We developed the derivatives into 3 dimensions. And then we said that because now we have a 3-dimensional space, we are going to need a new operator. And we called it the del operator. And Casey called it a del E. Remember when we were doing that? And then we said that this del operator, just like any other vector, can be applied to 3 different ways on other things. So when it applies on a scalar, when it applies on a vector, it can apply as a dot product or it can apply as a cross product. We called that when that del operator operates on a scalar, we called it a gradient. When it applies on a vector, we called it, when it was a dot product, we called it a divergence. And when it was a cross product, we called it a curl. We also said the gradient is equivalent to the slope. How low, how high? We said the divergence is how much something spreads. And we said curl was how much something twists or curls about an axis, correct? These are all the things that we talked about. Then we also did spherical coordinates. What do gradients, curls, and divergence become when we go to these dimensions? And we also did cylindrical coordinates, which were I, phi, z. And then I introduced you to this new thing called Laplacian, and I never told you what a Laplacian was. So today we're going to talk about where the Laplacian comes into the picture. So let's talk about that. So keep these 3 things in mind, right? So there was gradient, there was divergence, and there was curl. So keeping that in mind, I want to talk about second derivatives. So the question arises, what happens when I apply the del operator twice? So when we applied the first derivative, we got gradient, we got divergence, and we got curl. Now when I apply it again, what do I expect to happen? So this is what happens. Again, 3 things can happen. One would be the gradient. One would be the divergence. And one would be the curl, following the same pattern. So when I applied the del operator to make it into a gradient, I had to apply it to a scalar term. And that gave me the answer as a vector. Then I applied this del vector. I took it and I applied it to another vector. and I got a dot product with it, that gave me a scalar answer. And the last was when I applied it to a vector, I could cross it, and that answer came out to be a vector term. These were all our three possibilities from yesterday. Okay, now, what do I have to do if I have to apply this del operator again? Okay, so I will tell you, in this case, the answer is a vector. That means I can take both the divergence and the curl of this answer, which means the possibilities are I will get divergence of a gradient or a curl of the gradient. What would this look like? The divergence of a gradient. Del dot del t. What will this look like? Del cross del t. Remember, this t is a scalar by itself, right? This is a scalar. It's just a number, like the temperature of a room. Now, what about the divergence? For this case, can I take a curl of a scalar? Can I take a divergence of a divergence? So what's the only possibility left? I can only take the gradient of a divergence. And what would I write that as? Del dot E. And gradient is always a scalar, right? As a result, I will get a scalar number. This, they have found after multiple calculations and a lot of math, they tell you that this does not have a physical significance. And so we do not give it a name. And they just call it a gradient of a divergence. And it's just a number that you get out of it. And because it doesn't have a physical significance, we don't necessarily do more stuff with this. Okay, let's call this one 1, this 2, and this 3. And I'm going to do the curl also. Now, since the curl is a vector, what can the two possibilities be?
Divergence and a curl.
Very good. Divergence and a curl. So we could do which one should we do first? Okay, divergence first. So we'll do a divergence of the curl. And we could also do the curl of a curl. I'm going to call this number 4, and I'm going to call this number 5. What would the divergence of a curl look like? Well, divergence means it's a dot product, and curl means it's a cross product. And a curl of a curl means it's a cross E. With me so far? Excellent. Griffiths proves that this is always equal 0. Okay, now what about the curl of a curl? A curl of a curl is actually del E minus del squared E. That's the answer. So a del cross E reduces down to this.